This is CSE 455, Software Engineering, meeting you today on the 25th of May, Monday. First, I would like to greet everyone a happy Memorial Day, and I'd like to give gratitude to all those um, veterans who have given their lives today so that we will all be free. Okay, ready for our class? Let's begin. First, let's talk about deadlines. I want to say again that the SPMPs have been approved, all of them. That's very good for planning. And the software architecture and design documents are still being reviewed. And I see teams having difficulty coming up with the software architecture. This is just a reminder that I would like to see the derivation. There is a trace that I can point my finger on your design, starting from the deployment diagram to derive the high-level design from the deployment diagram or some root main component that you might have. That's okay. And then you begin your top-down design from the beginning, either deployment diagram or a root main component. And then you derive the low-level design from the high-level packet or component diagrams. So you can trace from the component diagrams of the deployment diagram the low-level design class diagrams from the high level. And then from the low-level design class diagrams, you derive the pseudocode and um, specify the critical functions and methods, not all of them, but the critical ones from the low-level design diagrams. So this is what you call top-down design or hierarchical decomposition. So from the hierarchical decomposition or top-down design, you can trace the derivation of the high-level design from the deployment diagram, and from the um, high-level design, you derive the low-level design, which is the class diagram, and then finally, you derive the methods and functions, important ones, from the low-level design. So I'd like to be able to trace my finger starting from the deployment diagram all the way down to the pseudocode where all of the above components and class diagrams were derived from. There shouldn't be any gap. There should be a continuity of the trace of where things were derived from. Now, if you are continuing a project, then you use reverse engineering. So you start from the class diagram because the source code is given. So you can actually um, identify all the classes that were used from the source code. And then from the class diagram, you begin composing uh, class diagrams into packages. This is a higher level composition of several classes into a package, and then composing packages into um, component diagrams. So packages now became um, component diagrams, and then finally composing component diagrams and trace it back to the deployment diagram where you have the software component that was identified in the SRS. So it's called reverse engineering because you're beginning from low level to high level. Uh, if you are starting from the from the deployment diagram down to the low-level design, you are doing what we call forward engineering, the normal process of top-down design. So see my lectures number 12, number 13, and number 14, where I discuss um, um, reverse engineering and forward engineering. Okay? All right. Continuing with the deadlines, the delivery and QA testing of iteration number 1 and prototype number 1 was due yesterday, 24th of May. So I'm reviewing the QA test reports that were filled up by the QA teams. So I will inform you what happened to your prototype 1 testing. The and there's an upcoming deadline that I would like to start to announce today. There will be a performance evaluation that is due on the 29th of May. That is this Friday. Performance evaluation is a step in our software development to evaluate how management consisting of the project manager, assistant project manager, how well did they manage the team, and the performance of the software engineers in the performance of development. So we are going to do that evaluation, and I'll show you later how to do the evaluation. And today is a significant milestone in our software process. Today we are launching the start of iteration number 2 or prototype 2 with a delivery date of the 10th of June, which is finals day. So we're coming to the close of the spring quarter, which will culminate in the delivery of your iteration 2 or prototype number 2 on finals day. Okay, so let me talk about performance evaluation. Okay, so let me show you the performance evaluation that we're going to do. Okay, so here I have a stick diagram of the developing teams. The management team, as you know, consists of the project managers and the assistant project manager. The two lead the whole team, and the software engineers consist of the team itself. So the software engineers will evaluate the management team. Okay, so the um, the software engineers will fill up a form called the leader survey, and the leader survey will evaluate the ability of the management team to manage the development. So every member of the team will have a separate evaluation for the project manager and the assistant project manager. So you will evaluate them separately. And here is the form that you are going to fill up. Okay, so the form is for the team lead. You put the name of the project manager or the assistant project manager, and here is what you're going to evaluate them for. The number one question is how well did the individual shown leadership in the team. Is the project manager or the assistant project manager able to motivate the team to work more? This is the ultimate test of leadership, when the leader can encourage to do more than what is expected from the team. Next level is, did the leadership able to move the team to do just what is necessary. So this is kind of fulfilling the basic requirements. Letter C, able to move the team to action, but with difficulty. So there is some difficulty in moving the team forward. And the team was, and the worst one is the team was drifting without any leadership at all. So rate them as A, B, C, or D. Okay. How about organizing the team? Did the leadership or the team lead or the project manager or assistant project manager was very well organized? Or it's just well organized, or somewhat organized, or poorly organized? So the choices are from excellent to poor, as what you can see here of how the project manager or assistant project manager organized the team. How about the task that was assigned to you? Is it very well defined, somewhat defined, or vaguely defined? And of course, the worst is vaguely defined. And if you don't understand the task that was assigned to you, then that's a fault of the management team of vaguely defining the task to you. How about communication skills? Did the project manager or the assistant project manager, is he an excellent, or he or she is an excellent communicator, or very good communicator, fair communicator, or poor communicator? So rate them according to this question. And anything that we didn't cover above, I give you a chance to write any of your comments. Okay? So that's what's going to be filled up by the software engineers for each of the project manager and the assistant project manager. Okay, so for the management, I mean the QA team, the leader survey is going to be just one, uh, just directed towards the team lead, because there is only um, um, one personnel that is assigned to be the team lead, and therefore you will only fill up for the QA team to evaluate your team lead. So the leader survey will be used in evaluating your team lead. Okay? All right. Now let's move on um, to the members. Okay. So here the management team, which consists of the PM and the APM, will together uh, um, uh, fill up a member survey of how the different teams or the different members of the team perform their duties. So there is a, um, a survey called member survey. So let me show you that member survey of uh, what it looks like. And here it is. So the member is being evaluated for completion of the assigned task. Was the member ahead of schedule, on time, a little late, or very late? So it is the performance of the member in the completion of the assigned task. Of course, the best is ahead of schedule and is able to perform some other functions. How about the quality of the work that was submitted? Did it exceed the requirements of the work? Does not need any revision? Needs minor revision? Or needs major revision? So the quality of work that was submitted ranged from the member exceeding the requirements to the task that was done needs major revision. Of course, you don't want major revision because that is a delay in the um, development of the project. How about team spirit? Is the uh, is the member very cooperative? He is a team player, cooperative, somewhat cooperative, or uncooperative. And this is actually one of the main complaints of a management team or team leads that the member is very uncooperative. And one of the signs of not cooperating is reply, non not replying to emails or Slack communication. So very hard to push the member to be part of the team. How about the work attitude towards the assigned task? Is the member very enthusiastic, eager beaver? Of course, this is kind of an informal evaluation, but you'll know if the member is an eager beaver, always looking for or um, would like to do the best job that he or she can do. Uh, Others are just so, just to complete the work, not really motivated or just don't care. And the don't care attitude is um, uh, very um, undesirable because if a member is not showing any care at all about the performance of the development of the software project, it could delay the project. And then any comments that you might have in with respect to this particular team member. Okay, so that's the member survey. I'm repeating again, the PM and the APM combined will write one member survey for every software engineer member in their team. Okay? And for the uh, QA team, the of course the member survey will just consist of just one because there is only one leadership in the QA, the team lead, and the team lead will uh, fill up one member survey for every member of the QA team. Okay, so that's the performance evaluation that I said you will need to submit by Friday. Okay, all right. Next uh, is the continuation of our uh, uh, subject of testing. Okay, there is two techniques that are used in testing, well known. One is called the white box testing, and the other is called the black box testing. And the white box testing is based on the knowledge of the internal workings of a program segment. Tests could be conducted, so you are testing actually all the pathways that you can select or all the pathways possible in a program segment and to select test cases so those pathways are actually tested. And um, the white box testing is usually used in unit testing of segments, of code, function, or a method or an entire class. It could be used there. And the let me show you the example that I have here on the a very simple example of a segment that shows just a simple path from a program segment. Okay, so here in this flowchart, you see a very simple program starts here, and from here it can have 5 possible paths. This is 1 to here. Here is 2 path. Here is 3 path. Here is 4 path. And then here is the 5 fifth path. Okay. And then from here, either it exits or goes back for another loop, and this loops 18 times. Okay, so if you count the possible number of paths that you can take here, it's for the first case there are 5 possible paths and you loop only once. The second possible case is you select one of the 5 and you loop 2 times. And so on and so forth up to 5 to the 18, which is the maximum number of times you will loop. And this is approximately 10 to the 12. If you're going to have 100% path checking, the number of possible paths here for 100% testing is 10 to the 12. So here you will see that in this very simple loop of 5 possible path plus the 18 possible loops, if you divide that 10 to the 12 possible path or total number of test case to test all possible paths divided by the total number of seconds in a year, 31,536,000 seconds. That is assuming that it takes you 1 second to finish one test case. It will take you 31,710 years. That is ridiculous, right? 1 second. Of course, the computer is very slow, but maybe let's have the computer a little bit, 1 order of magnitude, or maybe even 2 or 3 orders of magnitude. Let's say it can process 1 test case per millisecond. Okay. So 31,710 divided by 1,000, you get 31.71 years. Still ridiculous to test 100% of a simple loop to take you 31.71 years. Okay, let's get a much faster computer. Let us say the test case can be processed in 1 microsecond. That's 1/1,000,000 of a second. Even with this very fast computer, the whole 100% testing, it will take you 1.5 weeks. Still a very long time to test a very simple loop, okay? And of course, that is unacceptable. And so what I'm showing here it is really very hard to do 100% test case. So what can we do? We have to uh, find a way not to do 100% test case. Although there are automatic test case generators we have out there, and they generate test cases automatically and test it overnight. So very fast computers, computers that are able to process in a nanosecond instead of a microsecond are available now. But still, that is tremendous use of computing just to test a very simple loop. Okay, so how do we avoid having 100% test case testing? So there is a software metric that measures the logical complexity of a program segment, a function, or a class, or an object. This is called cyclomatic complexity. That's a measurement. And how do we define it? It's the number of independent paths in the basic set, and you have an upper bound for the number of tests to be executed to ensure that all statement is at least executed once. So this is a kind of a limitation that we don't need really 100% coverage of 100% of all test cases. As long as we can execute it at least once, that should be enough. Okay. So we determine independent path through the program, and introduce a new set of processing statement or a new condition. So independent path, we determine independent path in that program through this cyclomatic complexity. There is a graphical way of how to do that. And then we select test cases that will be used to force execution of this path at least once. Okay? That's the idea. So we don't get bogged down with that very long period for 100% test case and following every path in your program. Okay. All right. So here, let me show you a diagram that would okay. Here is a diagram of equivalence of a program that is written in some pseudocode. So we're not dealing with source code here. And we use what we call flow graph notation. So if you have in your pseudocode a sequence of execution of two instructions, we represent it in this diagram here, a sequential execution. Now, if there is an if statement, then the if statement either branches here or down here. And then somewhere it joins and then proceed. Okay. The while statement is represented as a loop here, and then by some condition it goes out. Okay. And the repeat until is a situation where you have a loop and then it exits afterwards. Okay. And then if you have case statement, so you have several cases that you are branching out. And so you choose one of these case and then you step out. So what this is showing is that any pseudocode can be um, can be uh, represented by a flow graph. Okay, so here is a flow graph of this pseudocode. Okay, so this pseudocode that you see over here is consisting of ordinary program constructs where you have a a big loop, a do forever, do while. That's the beginning, and that's the end. And then you have an execution, read the record. And then here you have an if statement. If record field is this, okay, and if it is true, you go here. Else, if this is true, you do the then. Else, you do this, and then perform some execution. This and if here is the scope of this if statement. And then and if here is the scope of this if statement. The end do here is the scope of do statement, as you see here. And then the last end is the end of the procedure of function. Okay, so if you numbered only the decision, don't number the execution. Execution, especially if it is sequential, doesn't count. All we count are where we do a branch. Okay, so here is a marking for 1. That's the beginning of this big loop, 1 and 8. And that is represented here in the flow graph as this one. From 1, I go out to 8. See that? Okay, that means the condition is not satisfied, or it is it's while record remain. If there are no records, you jump out, right? Okay, and if there are records, as long as there are records, I go inside the loop right here, right? Okay, so read the record doesn't count anything since it's an execution. So we mark number 2, the if record here, because that's a branching. So the if statement causes the program to branch. And 2 here represents, okay, here, that if the, while there are records, I'm going to execute the read record, but I don't show that here because it doesn't affect the branching. What affect the branching is number 2. If the record field is 1, then we go into 2, that is shown here. See that? Then, if it is true, then we go to 3, the then part. So 3 is represented here. And the then part has 2 executions, store in the buffer, increment the buffer. I don't count them because they are just execution. Okay. And when I am done there, I jump to 7B, right? So I go out here, 7B, right here, because the then is satisfied, and this is the if and if, okay? And so if I satisfy this, I jump out into 7B, which is the end of the big loop, okay? The big loop, undo, 7B, okay? And then I go back to number 1. So 7B goes back to number 1. We do the next record. Follow? Okay. Else, if, there's another if here. And so that is number 4. So that's number 4 here. Now remember, number 3 was the true situation if the record field is 1. And the next one, if it's false, if record field is not 1 and record field is number 2, then we go to 4, right? Number 4. So we have another if again here. And the if here is, if it is true, then it goes to number 5. Then reset the counter. So that's number 5. And otherwise, it goes to number 6. Process the record. Number 6. Okay. We don't number store in the file because it's not a branching. It's just execution. And they all end here. And if. And that end if is the scope of the if statement that you see here. So you have 7a. 7a is the ending of number 4. That's the limit of number 4. Okay? And then from 7a, it goes to 7b. That's the next one. Goes back again for the next cycle. And then finally, 8 is the end of the procedure. Okay? All right. So this pseudocode, written in some language, but following if construct, while construct, else if construct, and so on, all the programming language that you have can be represented by this pseudocode. It's called PDL. Okay? PDL. So the whole program can be represented by a flow graph. Okay, and this flow graph can be flow graph can be used to actually determine a formula that we can compute for the cyclomatic complexity. The cyclomatic complexity is very simple. The number of edges minus the number of nodes plus 2 equals the cyclomatic complexity. So you have that. Okay? So in our example of okay, I lost my cursor again. Here. Okay, so let's look at this. So it's the number of edges. So if you count, there will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, did we count all of them? That is going to be, let's count again. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9 edges. Okay, and how many nodes do we have? Well, we label here 7A and 7B, so there are 7A, 7B. Let me count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So let me go back to the, and there are 9 nodes. Oh, 11 edges. Okay. So 11 edges minus 9 nodes plus 2. E minus 9 plus 2 equals 4. So 4 is the uh, 4 is the cyclomatic count. Eleven edges. Let's do this again. I get lost. So this is 1. This is 2, right? 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? It's hard when you cannot see the pointer. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? Okay. So there are 11 edges. Minus 9 nodes. Remember, there's a 7 A and a 7B, 8, 9. 9 nodes plus 2 equals 4. So here, you're going to determine the number of paths that you should try in order to be able to test, select test cases, select test cases that, okay, I lost my cursor again. It's getting really annoying. Okay. Let me get that image again. Okay. So what are those paths? Okay. So one path is 1 through 8. Right? That's one path. The other path is 1, 2, 3, 7B, and then back again to the top. That's the second path. The other one is 1, 2, 4, 5, 7B, 7A, and then back to 1, and then 1 through 8. Okay. The other one is, the last one is 1, 2, 4, 6, 7A, 7B, go to 1, and then 1 out. Okay. So in the cyclomatic count, you have a kind of a idea of what test cases to try in order to test the um, the program. So you'll see that um, it's very simple sorting algorithm, and the sorting algorithm is um, it's a normal algorithm, and you don't really need to test all possible test cases for all the path going through the program. You know how difficult it is to actually have 100% coverage of all paths. Here, we cover only four paths. Okay, only four paths. That is all we need to exercise the path at least once. So you create test cases that you can um, use for 1 through 8. So 1 through 8, select test cases that would exercise 1 through 8. Select test case that would exercise the uh, uh, the algorithm following through 1, 2, 3, 7b, 1, and then 8. And then the next one is 1, 2, 4, 5, 7a, 7b, 1, and 8. And then the last one is 1, 2, 4, 6, 7a, 7b, 1 through 8. Okay? So you don't really need to proceed with a path that exercise all of them. All you need is uh, all you need is five. I mean four only. Okay. So there is an example I gave in the handout or here. Let me get that to you. So here I have an example of a, a pseudocode, and I want you to give me next meeting uh, the uh, um, the flow graph of this algorithm called averaging. Okay, so follow the example that you have before of determining the flow graph of this simple algorithm of sort, and determine the VG. Okay. Now here is an example of a compound logic. So here you have a if statement, A going over here. If it is whatever is the result, you go to the right branch, X, and then join here. And then over here, you have again another choice of choosing X, okay, also. So it is easy to simplify this graph here, that if A or B, so we can say A or B, then procedure X is done, because A and B, if A is true, we go X. If B is true, we also go to X. So why not put it together here in one uh, uh, procedure, and you perform X over here. Otherwise, if it is false, then we execute Y. So this is just a simplification of a flow graph to a simple one, rather than a complicated one by following this flow graph. Okay. So as I said, for those of you who would like to try it, uh, give me the flow graph, and next meeting I will give you the cyclomatic complexity measure. Okay. Next time I'll do that. Okay. All right. So let's move on. So try this algorithm here. Okay. Let me get rid of this and go back to the lecture. So there is a control structure testing. So here in the testing case here, we always see this kind of construct of a expression one, and there is a relational operator about E2. So E1 and E2 are arithmetic expression, and the relational operator is either less than or equal to, not equal to, greater or greater than, equal to. And the compound condition could be or, and, or not. Okay? So what are the test cases that you can try for control structure? Okay. Um, for the control structure, we will have the types of condition that you are going to try. Either you have a Boolean operator error, for the condition, a Boolean variable error, a Boolean parenthesis error, a relational operator error, or an arithmetic operator, arithmetic expression error. So the types of errors in a condition, you try all of these errors in that relational operation. So there could be error in the arithmetic expression, error in the parentheses, error in the variable, error in the relational, and so you try these types of errors in a condition. Okay, so these are the test cases you will try to test that error condition, relational error condition. Okay, now you have loop testing, and you always encounter loop testing uh, primarily primarily for um, uh, for the loop constructs. Okay, so let me get out of this. Okay. And let me get this kind of loop. All right. So in this loop, you have a simple loop where you have a decision, um, and you go here and then exit. On the other side, the operator is done, and then you test, and then you go back. That's a simple loop. Here is a nested loop. So a loop within a loop. Here is a concatenated loops. So you have a, uh, a loop here and then followed by another loop. And then here is what we call a spaghetti code, okay? Unstructured loops. And of course, we avoid these unstructured loops. The spaghetti code can lead to unpredictable uh, result because it's hard to trace uh, which loop is or which decision statement is being um, executed here. So for simple loops, here are the rules. Okay, the rules are uh, stated over here. So if it is a simple loop with maximum n iteration, one test case is to skip the loop entirely. So for a simple loop. So you have here skip the loop entirely, and that will be uh, the end of that test case. Okay. Another one is only one pass through. Okay, so only one gets through it. Sorry about that. Here it is. Just one pass through it. Two passes through the loop. Two passes. So you loop twice through the simple loop. And another one is M pass, where M is less than N. M is less than N. Okay? And then test case for N minus 1, just 1, less than the maximum, exactly N. One more than the normal N loops, maximum of N plus 1, passes through the loop. So these are the test cases you're going to try to test the simple loop. Okay? Now, how about for nested loops? And we have these nested loops that we always encounter in our algorithm or pseudocode. Okay? So for nested loop, start at the inner loop, set all other loops to minimum values. Okay? So here, for set the inner loop first. So for nested, you begin from the inner loop, while the other loops, the outside of it, is set to the minimum. Okay? What else? Conduct simple loop test for the innermost loop. And the innermost loop, we have set it at skipping it, passing through once, passing twice, passing n, times passing m less than n, and so on and so forth. So we do that while holding the outer loops at the minimum iteration. Okay? And add other tests for out of range or excluded values. And then work outward, keeping all other outer loops at a minimum value and other nested loops to typical values. So you work outward until all the loops have been tested. Okay. So here in this example here, you test the inner loop first. using simple loops, and then work outward from the inner loop to the next inner loop, while the outer loops are kept at a minimum. So work outward until you reach the outer loop. So simple loops will be used to test the um, inner loops. Okay? All right. Next one is concatenated loops. Okay? Concatenated. And concatenated loops are follows. Use simple loops if they are independent of each other, then use the simple loop uh, procedure. If they are not independent, then use the nested loop. So you keep one minimum while you apply simple loops onto one of them. And you start going, testing each loop um, uh, one after the other until you finish all the loops. And for unstructured loops, there is no other solution except to recode. Okay, you don't want spaghetti code. Okay, and it's hard to trace it in terms of debugging, so you have to recode and make it more structured. Okay, so that's I believe all my lesson for today, and we'll continue testing on the topic of testing next meeting. Okay, on Wednesday. Okay, so be safe and healthy.